In the first video on monads, we talked about the slogan that monads axiomatize algebraic structure, and we've seen some examples of algebraic structure. And so in this video, I want to concentrate on one particular example of algebraic structure, that of a monoid. And then I want to look at the particular kind of monoids, which are called the free monoids. Okay, so monoids are so common in computer science and computing and programming that it's really not so easy to know exactly where to start. And so I thought I start with a slogan that monoids axiomatize change of state. So monads axiomatize change of state. So obviously there are many different ways of thinking about monoids, but let's start with this. Monoids axiomatize change of state. And so a typical example would be that of a finite state machine or a deterministic finite automaton. So let me just draw a very small example here. So we have two states, and then we can move from one state to another state if we input a letter. So let's write little a here for a letter and say if we start in the state, let me call it 0, and if we start in 0 and we stay in 0 with an a, and we go to state number 1 with a b, and then let's say that if we are in 1, we stay in 1 with a b, and we go back to state number 0 with an a. So what we can observe about this structure here is that each letter really corresponds to a function on states. So maybe it's time to introduce some notation here. So sigma in our example is the set AB, and we also call it the alphabet. And the elements of the alphabet are also called letters, or maybe symbols, or input symbols. And then the set Q is the set of states, so I just call them 0 and 1 here. And this is the set of states. And so the picture then we see is really just a function from input symbols and states to states. In particular, every letter corresponds to a function. And so maybe I put a little line on top of the letter in order to say that now I mean the function which is associated to the letter. So just to be clear what that is in this example, right? So we have two states, 0 and 1, and then on input A, if I'm in 0, I stay in 0, and if I'm in 1, I go back to 0. So that's the function. So this is a simple example of change of state, finite automaton, finite state machine. And we see that it corresponds to, it gives us, essentially it consists of a set of functions acting on this state space. So if you think about this, what the mathematical structure of these functions is, and let me now switch to some generic notation f and g for functions. So I can compose functions, right? I can first move on the letter A, and then I can move on the letter B, for example. And if I can compose functions, I can also compose three functions. And then I can do this in two different ways, right? So I can first compose G and H, and then I can compose the result with F, or I can first compose F with G, and then I can compose the result with H. And so if you think of state change, then really where we put the parentheses shouldn't matter at all. So this is an equation, a law, which is called associativity. And then in order to define what a monoid is, we also consider identity functions. So this is the function that doesn't change state, right? And we call it, I write it as ID to remind us of identity. And then we get two more equations, which are saying that if I compose with the identity function, then I get the same function. So these two laws are called identity. And so that's really what a monoid is. So let me now switch to the definition. So definition. So a monoid and now what are the ingredients of a monoid? I have a set M and I have a constant, I call it E, and I have a binary operation, so it's usually called multiplication. It was composition in the previous example. So a set, a constant, a binary operation, and it needs to satisfy, a monoid satisfies the equations, and it's really the same equations as we've just seen. So just with a new notation now. So let me now use the standard names for variables x, y, z, right? So x and y and z, and this is for all x, y, z in M. For all elements of the monoid, this equation has to hold. And then also we have the equation that E multiplied with x is x, and x multiplied with E is also x. So a monoid is a mathematical structure which is defined by operations, a neutral element, and a binary multiplication satisfying these three equations. So really here we are a bit more precise about our slogan from the first lecture, that algebraic structure is given by operations and equations. Okay, so our next example of a monoid is the free monoid, but maybe just very quickly, I should say that we can take the natural numbers with 1 and multiplication as an example of a monoid, or we can take the natural numbers with 0 and addition as a monoid, or we can take the integers also either with addition or multiplication, and we can take other numbers like fraction and so on. So really there are many more examples for monoids other than just what we get from composing functions that act on an automaton. But let's get back to the automaton. So we said that essentially it's a map that takes letters and states and maps it to states. But really what we want is we want to run an automaton not only on single letters but on words. And so words are really an important construction, and so there's this kind of standard notation, sometimes called the Kleene star. So this is the Kleene star, and we use it to decorate the set sigma, the alphabet, when we want to really denote all the words over the alphabet. Right, so whenever we have an automaton with a transition function that tells us how to act, how a single letter acts on the state space, we can also inductively define from that a function that reads a whole word and changes the state according. And so sigma star is called the set of words, or the set of lists, or the set of strings, or the set of sequences. So this is such an important data structure, words, lists, strings, sequences, that it comes under various different names. And so this is really what mathematicians call the free monoid over sigma. So you may ask, why do I introduce unfamiliar terminology for something that is so familiar? It's just words or lists or strings or sequences. And the reason is that in the end, we want to understand monads as axiomatizing algebraic structure in general. And so if you're going beyond monoids, what will be the analog of the set of all words, right? So that's maybe not so immediately clear. And it will turn out that algebraic structures in general have free algebraic structures. So there will always be a free algebra. So let's get used to this terminology already now. So the free monoid is really just the set of words or lists or strings or sequences. And in the next video, what we're going to do is we're going to study the structure of the free monoid, and we will extract from this structure those operations and equations from this structure which will transfer to algebraic structure in general. So we will see our first monads in the next video, the free monoid monad or the list monad. Thanks for watching.